So we can quantify, we can actually calculate what is going to be the new boiling point for the solution. We can do the same thing for freezing point, and just like if you know the change, then you can figure out what is going to be the new freezing point, or new boiling point. And the calculation itself is quite straightforward, and knowing the definition, knowing the relationship there, you should be able to do the calculation. Okay. Another thing that here is that the mass of the ethylene glycol, the antifreeze that you use, okay, and when you add antifreeze to water, make a solution there. Now, how much do you need? Well, antifreeze, ethylene glycol, whatever you added in there, antifreeze is one of the applications. Whatever you put in water there, when you have the solution, well, the boiling point of the solution is going to be higher and will be increased there. Okay, so in this case, ethylene glycol, if you put it in water there, 125 grams of water, you add a certain amount in there. Now, in this case, we know we want to have the boiling point elevated by 1 degree. The boiling point of pure water is 100 degrees. We want it to be 101 degree. So the change is 1 degree there. So again, delta TB in this case now will be 1 degree. And that equals to 0.512, and this is the boiling point. Constant there, and then times the molality. Molality is the number of moles per kilogram. We have 125 gram of water, 0.125 kilogram of water. Okay, and then how many grams of ethylene glycol do we need to add in there? Well, we don't know. X gram times each mole is equivalent to 62 grams. Okay, so if you look at this equation there, the only unknown in there is your X, and that's the mass there. And you plug in the number and do the calculations there, 15 grams. Okay, so this is another type of calculation that we do need you to be able to do. And using the relationship of the freezing point pressure and boiling point elevation equals to K times molality. And when you know the definition of molality, when you're given the K there, you can do calculation. And of course, we can also ask you to figure out the constant, giving you all the other information there. Okay, so that's the type of calculation that that you could you should expect when you deal with these different types of properties there. And the last colligated property that we want to mention here is what we call osmosis. Now, if you do, you can actually do this experiment at home. And get a fresh egg and cooked, of course. And you want to make sure that you wash the egg there. Now, if you take that egg, you put it into vinegar. Well, you can use pure vinegar, or white vinegar, or you can use pure acetic acid. Now, the acid will actually eat out or dissolve the calcium carbonate. One of the things that you may need to remember there is that when you for the solubility, rules of solubility that we talked about yesterday, this is something that you will, solubility rules there, and something that you will see on the final exam there. And we talked about it in chapter 4, when I said you don't have to memorize them at that time. But when you prepare for the final exam there, you do need to pay attention to the solubility rules there. And there is a particular slide on Canvas there. When you click on the final exam there, you will see that slide. Okay, that's information you need to remember. If you don't want to memorize it, you can put it on your index card when you go to the final exam. All right. So osmosis here, and if you put an egg in acetic acid, you will be able to remove the calcium carbonate and remove the hard shell. Okay. Now what's left there is the membrane wrapping up the whatever is inside the egg. That membrane is what we call the semi-permeable membrane. It will only allow water molecules to go in and out. But whatever is dissolved in the water there, whether you have organic matters, there are proteins and all the others, and it will not be able to come out. Okay? So in this case, after you remove the hard shell of the egg, if you put it into water, pure water, we would consider on the outside of the egg, if you put it in pure water there, and there's a higher concentration of water compared to what's inside. So in this case, osmosis will happen. The water molecules will make an attempt to get into the egg to equalize the concentration of water on both sides. The result of that, you see the egg start to swell because more water is getting in there. Okay? And then, however, if you take that same egg and you put it into corn syrup, Now, corn syrup has lower water concentration or lower content compared to what's inside the egg. So in this case, the water inside the egg will make an attempt to move out of it, and in order to equalize the water concentration, if you will. So you see the eggs start to shrink. So this is the process of osmosis there. Osmosis is when you have two different solutions, two different liquids being separated by a semi-permeable membrane, which only allows the water molecules, small molecules like water molecule, to move in and out. Well, if you do that, if you mix them together, if you put them together, separate them by a semi-permeable membrane, the solvent will move from the higher concentration side to the lower concentration side in an attempt to equalize the concentration. Okay, so in this case, we have in this diagram there, we have the pure solvent on one side, on the left side, and we have the solution. And if you separate the two by a semi-permeable membrane there, and the water molecule will, well, in this case, solvent, will be able to move in and out in order to reach an equal concentration there. Okay, so the solvent molecules move from the pure solvent to the solution side in order to equalize with the concentration. And when that happens, you will actually generate a little bit of pressure, and this is what we call the osmotic pressure. Now, say if you have a semi-permeable membrane there, you make it a bag there, and you put some sugar solution in it, 95% water, 5% sugar. Okay. Now, if you take that bag and you dip it into pure water, on the outside you have 100% water. On the inside you have 5% water, 5% sugar, and then 95% water. So you have a lower concentration of water inside the bag. Now, if you do that, if you dip that bag into pure water there, over time you will see water molecules will get through the semi-permeable membrane, and then get into the bag there. You will see a water column being pushed up along this glass tubing there. The water column will actually generate a pressure. This pressure is what we call the height of the column, and we can actually calculate how much pressure we have there. So this pressure is what we call the osmotic pressure. It's a very important thing there. We can actually quantify the osmotic pressure. I equals to mRT. And this M is supposed to be molality, moles per kilogram of solvent there. mRT is supposed to be a small m there. R is the gas constant, T is the temperature. So you can see the osmotic pressure, we can calculate osmotic pressure and using this equation. Now, what's the importance of osmotic pressure? Keeping the solution that we're trying to mix with the same osmotic pressure. Well, the importance here is that if you ever notice that when you go to the hospital there and when they give you an IV bag, it's not pure water that they use to dissolve the drug in the IV bag when they put it on patients there. And it's always says 0.9% sodium chloride. The reason for that is because if you use pure water, okay, and you dissolve the drug, and the drug gets into your bloodstream there, while pure water has a higher concentration of water compared to whatever is inside the cell. In that case, pure water will make an attempt to get into the cell to equalize the concentration. If that happens, then the cell is going to swell. And eventually, if you have enough quantity there, you're going to rupture the cell and you're going to kill the patient. 0.9% sodium chloride. 0.9% sodium chloride solution has the same osmotic pressure as the whatever is dissolved inside your cell. So using this particular solution and to dissolve your medication will prevent situations like higher concentration, higher